I'm going to talk about the ICRU Report 95, which has as a topic the operational quantities for external radiation exposure. And especially I highlight what is going to change for radiation protection, but this includes calibration. So it is also important for the representatives of secondary standard laboratories or even primary standards. Now I have to, what's going on? Ah, here, good. The ICRU Report 95 has been published in 2020 after quite some long time of work on it, which was also unfortunately overshadowed by the premature death of Professor Dietze from PTB, who was one of the persons who triggered this report. And after this loss, the report committee had to reassemble and start not really from scratch, but really take up his ideas and continue without him. The report is introducing the previous quantities which have been defined in the ICRU Report 39 and 51. It then introduces the definitions of the operational quantities for external exposure, the new ones. It explains how conversion coefficients from physical field quantities to these new dose quantities are calculated. And it highlights a few practical consequences. This was done at the status of the writing of the report. There is already more known than is written in this report, and I will give a few hints to what different groups are working on these practical consequences in this talk. And then there are very extensive appendices which give the values of conversion coefficients for many particles, many energies, and explain briefly the computer codes that have been used by the report committee members and by its consultants to calculate the conversion coefficients. This talk is having a few chapters which start with a brief introduction into protection and operational quantities. Then I highlight the present operational quantities, as I said before, defined in ICRU reports 39 and 51, and conversion coefficients were published in report 57. Then I explain the switch to the new quantities in the report 95. I explain how the conversion coefficients energy dependent will change, and then highlight a few of the consequences about dosimetry in real radiation fields, calibration, and dosimeter response. And then finally, I have a very short summary. So in radiation protection, we have two quantities. I start with the protection quantities, which are defined by the ICRP, the International Commission on Radiological Protection. These quantities have been defined to compare radiation detriments with limits and also to enable optimization. And this has been crystallized in the 80s and then finally published in 1990 in ICRP Report 60. The effective dose is a quantity which is a unifying concept to estimate the radiation detriment from both external and internal exposure. It's based on the mean organ dose from a different radiation type. And then the mean organ dose is added up over all radiation types and over all tissues, and tissue is a surrogate or a synonym for organ, over the human body. This has been found as a good compromise to estimate radiation detriment in the range of doses which are important for stochastic effects, which means well below 100 millisievert. The effective dose is not applicable to high doses. There we have to go again to the organ dose and eventually to the organ equivalent dose. I will come to this a little bit later. And very important, you have to remember that dose limits and constraints are expressed in protection quantities. If you are used to compare the reading of a personal dosimeter and personal equivalent dose with the limit, then it simply comes from the simplification that one uses personal dose or personal dose equivalent as a replacement value for effective dose when the dose is not too high, say a few millisieverts. The protection quantities, the values of protection quantities in specific fields, or as I can say also the conversion coefficients from the field quantity to the protection quantity, is described in the ICRP report 116, and it builds heavily on the phantoms, the voxel phantoms, which have been described in ICRP report 110. One does a numerical calculation with plane parallel and isotropic radiation fields, where one numerically irradiates these bodies, these voxel phantoms, and then does exactly the calculation as listed on the previous page, which means one adds up the mean organ dose multiplied with the radiation and the tissue weighting factors, and then the sum of this gives the effective dose after averaging over the male and the female body. For the eye lens, the protection quantity is the equivalent dose to the eye lens, which is calculated with the Dietze and Behrens eye phantom, which is inserted into a very simple humanoid phantom, which is only there for backscatter calculation. And for the skin, which cannot be well reproduced in the voxel phantom because it is too thin, or we can also say because the voxel resolution is too coarse, we have a very basic phantom which has a 1 liter volume, 10 by 10 by 10 centimeters, in which one calculates the absorbed dose in a 0.07 millimeter depth to get values for the local skin dose. These are the protection quantities as they are defined by the ICRP. Now, why does one need operational quantities? As you have seen, the protection quantities are defined as an average over an extended volume, the organ or the body. In particular, the effective dose is an average over a whole mannequin. And if you do not want to carry around a measurement instrument which has the size and the weight of a human body, you can in principle not measure it, and that would be very unpractical. Therefore, we come to the realization that only quantities which are defined in a point are measurable by an instrument, and the ICRU is traditionally defining the measurable quantities in radiation protection. In ICRU report 39, the dose equivalent has been defined as the product of the absorbed dose in a certain depth multiplied with the quality factor. We will come to the depth on the next slide. This is then called the operational quantity. Operational because it can be put into operation with measurement instruments and personal dosimeters. Very important, we have an absorbed dose and a quality factor. The quality factor depends on the LET and is defined also in a specific ICRU report. The calculation of these quantities, of the conversion coefficients for these quantities, is progressing in simplified mathematical phantoms, simple geometrical bodies. For area monitoring, we have the ICRU sphere, which is a 30 centimeter diameter sphere. And for personal monitoring, we have slab and cylinder phantoms, which are representing either the trunk, the head, or the arm and fingers, so the extremities. These phantoms are made from the so-called ICRU 4-component tissue surrogate, which is a simple chemical composition, which can unfortunately not be represented in real because it wouldn't be chemically stable. It's therefore only a numerical help. And these phantoms for the calculation of the present operational quantities exist only in numerical fashion. They shall not be confounded with the calibration phantoms that you know from the lab and which are for a different purpose that I will explain a bit later. I had shown before that there is a dose which is determined in a certain depth, and the depth is 10 millimeters for the dose to the whole body, 3 millimeters for the dose to the eye, and 0.07 millimeters for the dose to the extremities and the skin. So here I have made a plot in which we can see the relation of the present quantities. On top, we have the physical field quantities, the fluents, the karma in air, or the absorbed dose for respectively neutrons, photons, and electrons. And here I explain how we come to the effective dose and its measurable surrogates as operational quantity. The effective dose is calculated with the anthropomorphic phantoms. And there we have for specific radiation directions, conversion coefficients HE for a given energy of a particle and an incident direction. And the incident directions are listed here: forward, backward, backward, forward, left lateral, right lateral, rotational, ISO, and then there is a few ISO half spheres from the top or the bottom still available. With this one calculates the effective dose and the conversion factors of the effective dose for these radiation fields. For the operational quantities, on the contrary, one has the two quantities: ambient dose equivalent for ambient or measurements and personal dose equivalent for personal dosimeters. And the calculation proceeds with geometric phantoms. And in this calculation, we have on one hand the geometric phantoms, and on the other hand, we also have the Q from L function, whereas here we have the weighting factors, as I showed before. So therefore, it should not surprise us that with all the differences in the two branches of our radiation protection system for protection quantities and measurable quantities, we do not find very often a numerical coherence between the quantities on the protection side and on the operational side for the same radiation field. There is an additional difficulty, which is to measure these quantities with an instrument which has, again, another response, which depends on the energy and the angle. And this is coming in as an additional difficulty. I come to that a bit later. Now, what changes for the operational quantities? Seeing that the anthropomorphic phantoms are used for the calculation of effective dose, the ICRU report committee decided that we change from the numerical calculation phantoms for the operational quantities to the anthropomorphic phantoms with the tissue and radiation weighting factors. That will give a better approximation of E simply by definition. A few other changes in the report concern that the quantities which limit tissue effects, the local dose to skin and to eye, are now expressed as absorbed doses and not longer as equivalent doses. We list much more radiation types, like, for example, positrons, protons, pions. We cover a much wider energy range. And these two things are owed to the fact that nowadays more and more accelerators enter the field of radiation protection. And I'm not thinking so much about accelerators for particle physics research, but also in the medical application. And the quantities for photons have been calculated with full electron transport, whereas in the conversion coefficients in ICRU 57 and ICRP 74 were assumed to be with secondary electron equilibrium. This is a real change of the paradigm. Instead of taking a physical quantity, an absorbed dose, multiplied with a quality factor to receive the operational quantity H, we now take as a physical quantity the fluence of the field and multiply it with the conversion coefficient. The conversion coefficient is in turn calculated from the effective dose divided by the fluence of the field at different predefined directions. This looks a little bit like a circular definition, what I show here, but I think you will get the feeling of it on the next slides. So we define the conversion coefficients only for a certain number of incident directions. And for these, we are able then to give these conversion coefficients from the fluence. The same can be said for the gamma and air for photons. So what does this imply for whole body dosimetry? The present quantity for whole body dosimetry is the personal dose equivalent HP10, which is calculated as the dose in 10 millimeter depth in a slab phantom, multiplied with the quality factor depending on the LET. It's 10 millimeter under the center of the ICRU 4-component tissue slab, and one has to make a so-called expanded radiation field, which is self-similar over a large region of space in which this phantom is embedded. And we now switch to the so-called personal dose, which we calculate as the weighted sum with the radiation weighting factors WR and WT of the organ doses in the anthropomorph phantom. And we use for that plane parallel radiation fields from defined directions. For the personal dose, we don't only use the AP, PA, left lateral and right lateral, but we do fields, we have given calibration conversion coefficients for angles in steps of 15 degrees, which allow to assess the performance of personal dosimeters under oblique incidence of the radiation. Now I will show what that has as a consequence for the effective dose, the HP10 and the HP for photons. So here on these two curves, we see the effective dose in black under AP direction and in blue under the isotropic irradiation. This curve are the conversion coefficients to personal dose equivalent in 10 millimeter depth under 0 degrees with the Kerma approximation as they are published in ICRU 57 and ICRP 74. You can make two observations. We have an overestimation at low energies. This is 20 to 30 kilo electron volt. This comes from the fact that in lower energies deposit more energy in 10 millimeter depth as they would in the whole anthropomorphic phantom, which is the basis of the effective dose. And we have an overestimation at high energies, which comes from the assumption of the Kerma approximation. If one calculates these conversion coefficients by using the full electron transport, then this curve is resulting, which still has an overexposure at the low energies and an underestimation at high energies. And now we come to the HP under 0 degrees. And this is numerically perfectly equivalent with effective dose in AP direction, because 0 degree is anterior posterior, and we use exactly the same phantom, exactly the same weighting coefficients. We also have conversion coefficients for AP for a rotational and for an isotropic incidence. And you could see then that they fit very well also. What changes in area or ambient dosimetry? Here, the present quantity is the so-called ambient dose equivalent, H*10, and it's calculated with the same recipe. You take the dose in 10 millimeter depth, this time in the ICRU sphere, on the axis of the incidence of the radiation, multiply it with the Q from L, and you get the ambient dose equivalent. Here, you have to assume a so-called expanded and aligned field, which means that all radiation field components are assembled under 0 degrees. This is a maximizing prescription, which shall make obvious that this quantity is conservative under whatever direction the radiation field is having. It means that for measuring it correctly, you need an isotropic detector with an isotropic response, which can only partially be fulfilled. This will be replaced with ambient dose. And here we take the maximum of the effective dose over the directional coefficients listed in ICRP report 160. So we look at the conversion coefficients for AP, PA, left lateral, right lateral, and so on at a given energy. We pick the highest of them and multiply it with the field quantity fluence. And there is again AP, PA, and the 4 other directions. I show you what happens for neutrons. So here we have a whole family of curves of conversion coefficients from fluence to effective dose for neutrons. The black one is AP, and then there is different shades of blue, which are unfortunately a bit difficult to recognize. PA, lateral, isotropic, and rotational. And now I overimpose the curve of the conversion coefficient for H*10. We see that there is an overestimation at epithermal neutrons, but we all know that this is not a great concern because the conversion coefficients is low and epithermal neutrons are usually not very present in real existing radiation fields. We have an overestimation in the range of the fast neutrons between 100 keV and a few MeV, This is already of more concern. And then we have things which are wiggling around the curves at very high energies. This is, by the way, the area where the practitioners of radiation protection dosimetry were dissatisfied the first time with the quantity H*10. This is a, let's say, it's not a problem when you know it, but when you just hold a measurement instrument into a field at an accelerator, you will clearly underestimate the contribution of the neutrons. This was one of the triggers why the ICRU set out to think about new possibilities for definition. The new quantity, H star, is now the curve which is always on the highest of this family of curves and is therefore automatically by definition conservative. So therefore we have achieved the maximization with a, we think, simpler prescription as the so-called expanded and aligned field, which is very difficult to realize in nature. For Lens dosimetry, we change from the personal dose equivalent HP3, the depth, the dose in 3 millimeter depth in the 20 centimeter square cylinder. This is a cylinder which has the same diameter as height, multiplied with the quality factor depending on the LET. We are now changing to local absorbed dose to the Lens, D-Lens. And this is very important. This is an absorbed dose in the Lens. And the Lens is the Behrens-Dietze model. And this, of course, is an important change because if you had calculated HP3 for neutrons, you would have had a Q from L, which is different from 1. In the future, there is no Q from L anymore. You just take the absorbed dose. This comes from the consideration that tissue effects, including cataracts, seem to be depending more on the absorbed dose than on the equivalent dose. This is at least the state of science at the moment, as it was perceived by the ICRU. We see here the two curves for the protection quantity and the HP3, and the new operational quantity, the green curve, fits, of course, perfectly on the protection quantity. And then there's also a yellow curve, which is for positrons, because we said we may have positron emitters for which personnel has to be protected, and we calculated conversion coefficients for positrons. This is simply coming from the fact that a low energy positron will probably annihilate in air or in the very first layers of the Lens, and then emit 2 gammas and have then a constant conversion coefficient, still higher than that for electrons. I'm not sure that this is very relevant. Extremity dosimetry, we have only made cosmetic changes. At the moment, they are calculated in cylinder phantoms for the finger and the wrist or the arm, which are done with ICRU tissue of 1 gram per cubic centimeter. We have changed the density of this tissue to 1.11 grams per cubic centimeter, which would include the density of the bone in the finger or in the wrist. And we have covered it with a 2 millimeter layer of skin tissue, which has the formulation of the ICRP skin tissue from the report 160, which describes the phantoms. However, as I said, these are cosmetic changes, and the conversion coefficients between HP007 and D local skin are hardly different, at least for photons and electrons, where the quality factor is 1. And you see again the curves for the rod phantom for electrons. What happens? There's something, this hasn't, okay, there is the curves for the protection quantity, no, for the old quantity HP0.07, and then for the D local skin on the rod for the electrons, and again for positrons. There are no changes with practical impact, and the only change is, as I said, is in the definition that we now quote this as a dose and no longer as a dose equivalent. Here I come back to the scheme, which explains a little bit the relation of the different quantities. Starting again from the physical quantities, ICRP, on the ICRP side, nothing changes. On the ICRU side, on the contrary, we have replaced the quantities by ambient dose and personal dose, for which the conversion coefficients are calculated in the anthropomorphic phantoms with the same geometry and with the same conversion, with the same weighting factors as the effective dose quantity. And therefore, we have at many places under selected directions and energies for many particles, we have a numerical equivalence. As I showed before, you have seen that the quantity HP under 0 degrees is identical to effective dose in AP direction for a given particle, as one example. This, of course, doesn't solve the difficulty of measuring these quantities, and one cannot expect that a new definition of a quantity will solve all the measurement problems that we have in radiation protection. What will be the consequences of this change? There are 3 sections to this part here. I explain some consequences of measurements that one does in real radiation fields. I talk about the calibration of dosimeters, and then building upon the calibration, I can talk about the response of dosimeters. Here, I have again shown the comparison plot between personal dose equivalent in the red curve and personal dose in ICRU 95. Here is written Report Committee 26. This was the name of the report committee. I should correct it there. And you see, why do I do this with camera? Because you can have the y-axis in linear scale and you see better than on the double logarithmic scales. One sees that over a wide range of energies between 100 keV and say 3 MeV, which is a typical range of emissions from radioisotopes, which are a problem in nuclear applications, the personal dose is about 86% of the personal dose equivalent. This is the measured value of personal dose. At low energy X-rays, for example, backscatter from a patient in interventional radiology, at some energies, around 20 keV, there's a factor of 5 difference. I talked about that before already. I come here to these low energy X-ray spectra. Here is a high dose rate spectrum from the H0 series defined by ISO with the 20 kilovolt tube voltage. The blue curve is the fluence spectrum. The yellow curve is the fluence spectrum weighted with the H*10 conversion coefficients, and the green with the H* conversion coefficients. The area under the curve is the dose, or the dose equivalent. You see immediately that, of course, the area under the orange curve is much higher than that under the green curve. In more realistic spectra than these calibration spectra, the so-called diagnostic X-ray calibration spectra, which are relatively broad, you can also see that the upper curve is H*10 and the lower curve is H*. And here should have been a 0.5. I don't know what happened. The H* is about half of H*10 in these broad spectra. This comes from the fact that in broad spectra, such singularity effects at one specific energy are always smeared out. This may have an influence on the dose of medical personnel who works in interventional radiology, and this is still under study at the moment. I'm trying to make some calculations on that in my free time. Here is a study that I did together with a colleague from me at CERN, with Mr. Markus Widorski, and we have published this in the International Particle Accelerator Conference of this year, where we have analyzed radiation fields at particle accelerators. We selected the lowest energy CERN accelerator, which has 160 MeV protons, because this would be also applicable to facilities like proton therapy facilities. The study has 2 parts. There is a generic study for 100 MeV, 1 and 10 GeV protons on a target, and the realistic study for the 160 MeV proton accelerator. In the generic study, the iron target is bombarded with protons of the energies indicated here, and during the irradiation, the prompt radiation is scored behind a 2-meter concrete wall, which could be the place where personnel is working. Then in the Monte Carlo calculation, one lets a certain time pass and scores the decay radiation, which would be exposing personnel who have to go in the accelerator to repair components if it fails. We see here the spectra and the values of H star and H star 10, or rather the ratio of H star to H star 10 for the prompt radiation. On top, you see a neutron spectrum in green, and on the bottom, a proton spectrum also in green. And then overimposed are the conversion coefficients in blue for the quantity H star 10 and in red for H star. The ratio of H star to H star 10 is practically equal at the low energy of 100 MeV, but becomes higher and higher up to 1.2 approximately for higher energies. This comes from the fact that neutrons start to dominate the dose, and from 1 GeV on, the H star is higher than H star 10, because for neutrons, protons, and gammas, this is simply an observational fact from the conversion coefficient curves. But 20% is not as much as one could fear, and would not bring us to change our radiation protection philosophy at the accelerator centers. The activation study gives a result in a direction that we can expect from the comparison of the conversion curves for photons and electrons. You see on top the photon spectrum in green, on the bottom the electron spectrum, and again in blue and red the conversion coefficients for the old and the new formulation. I start with the photons. We have again the about 86% value of H star over H star 10, which means H star is smaller than H star 10 by about 15%, which is typical for radionuclides. For electrons, however, H star is quite a bit bigger because it takes into account electrons of much lower energy. H star 10 for electrons has zero contribution below 2 MeV, and there are not many emitters which have 2 MeV, as you can see from the spectrum. So there we can expect that pure electron emitters will certainly have higher dose values with the new quantities than nowadays. Whereas for photons, which are much more predominant in workplaces, the changes are benign in the 15% range. For the dump of the linear accelerator, we have similar results. The dump, we have first scored the prompt radiation, and you see the ratio between H star and H star 10. In forward direction, it is bigger than 1 because it is dominated by high energetic particles. In backward direction, you have backscattering and multiple scattering of particles which become subsequently lower and lower energy. And there you have H star smaller than H star 10. For the activation, we have again, I just point to the plot here on the bottom, a convergence of all the curves which have been measured numerically. I remind, this is all numerical studies. We haven't had any instruments yet for these new quantities. At the different places of the beam dump, we have at the beginning, at short decay times, a ratio of 90%, where the dose rate is still dominated by short-lived gamma emitters, which often have high energies. But as soon as about 1 day, 1 week has passed, they all converge to the canonical value of 0.86 as a comparison between the new quantity and the present quantity. Now, the good news for people involved in calibration is that the calibration procedure doesn't change. It is still the same song. You determine the reference point in a calibration field. At this point, one determines with suitable primary detectors or secondary standards the gamma and air for photons, the fluence for neutrons, or the absorbed dose for electrons. Then one calculates the operational quantity by multiplying the field quantity with the conversion coefficient, as given here. And you place the dosimeter at the reference point, and don't forget to put calibration phantom if it's a personal dosimeter to give the necessary backscattering effect of the trunk. And then for photons, in addition, you have to assure secondary electron equilibrium to have reproducible conditions. This whole obligation to calibrate photons in secondary electron equilibrium comes from the need that in a calibration facility, you need to be reproducible from Braunschweig over Paris to Denver and God knows what else calibration facilities are there at different places, at different height over sea level and so on, and in different calibration labs where the secondary electron spectrum of the pure calibration source could be very different. But by placing the so-called build-up plate in front of the dosimeter, which is either mounted on the phantom or for certain types not, you create artificially secondary electron equilibrium, and you can compare the calibration coefficients obtained in any calibration laboratory in the world. The ICRU 57 conversion coefficients, you didn't have to select anything because they were calculated in the so-called Kermer approximation, which assumes secondary electron equilibrium. However, as I said before, ICRU has now decided to publish in the main body of the report calibration coefficients for with full electron transport, because they can be used in other applications where the full radiation field is known with all its components, for example, in Monte Carlo calculations. Therefore, for calibration situations, you have to use the conversion coefficients from Annex 5, where secondary electron equilibrium is assumed. I show now in these curves the effect on the calibration in the quantities d islands and d local skin. On the left, you have the view graph with the blue curve in the dose to the islands with full transport from the main body of the report, and the one with secondary electron equilibrium from the annex. The same for HP 0.07. And now I overlay the present quantities HP3 and HP 0.07. On the right side, you could hardly see anything, only the curve has changed to gray. As I said before, the two curves, the phantom change between HP 0.07 and D local skin was more or less cosmetic. And therefore, if we use the same calculation prescription with secondary electron equilibrium, we will get the same results, which you see clearly verified here. For the islands, you have a good coverage for most of the energy and then some deviations at low energies. But we can expect that we can use dosimeters which measure HP 0.07 nowadays well, but they will also be good dosimeters for the local skin in the future. And for islands dosimeters, there is a very good hope that it will also work. I will show examples later. Voila. Okay, here's the conclusion. For HP, unfortunately, this trick doesn't work. Here we have again the blue curve with full transport and the orange curve with a single secondary electron equilibrium, only up to 10 MeV, and the difference is not very high. And here is the present curve HP 10 with secondary electron equilibrium, and you see again that the energy-dependent response function of whole body dosimeters must be modified at low energies to be useful for the new quantities. I come now to the response of dosimeters. The response is defined as the dose indication of a dosimeter divided by the conventional true value of the radiation field. When we change the quantity, the dose indication remains the same. The needle of a Geiger-Müller counter will point to the same number if I take a very old-fashioned instrument. And then I can simply calculate the response of a dosimeter in the new quantity by this substitution formula, the response in the new quantity is the response in the old quantity multiplied with the ratio of the conversion coefficient. And this I have been doing after the publication of the report with a number of dosimeter types to evaluate what happens with present dosimeters which are used in practice and how they can be used for the new quantities. I spare myself to show a skin dosimeter or extremity dosimeter because I hope you have seen that the two calibration curves are so similar that there is no doubt that the HP07 dosimeter of nowadays will work for D-local skin. Here's an Lens dosimeter, which is commercially available. And as I said before, at low energies, there is some deviation. But one could, for example, calibrate at the reference point and then use an arbitrary correction factor. And this I have really done by playing around with the curve. There is no fitting algorithm or so involved. When you reduce this then by 0.94, you get a very good energy response of this I dosimeter for the new quantity. So for I dosimeters, which are good for nowadays quantity for photons, there's a good hope that they will also work with the new quantities. Of course, that's not the case for personal dosimeters for whole body radiation because of the strong over-response at 20, 30 keV at low gamma energies. Here is a dosimeter based on OSL detectors and on the bottom on thermoluminescent detectors. And each time you see that they would show a high overestimation of personal dose at these low energies. And you cannot correct that by applying a correction factor. Curves are by far too different. So one would have to redesign either the filter or for dosimeters which use more than one detector, the algorithm which is used to calculate the dose from the different indications of the detectors. This has been confirmed also by an intercomparison of Italian dosimetry services, which we have published recently in the Journal of Radiological Protection, where you see that at the lower, the broad spectra, which have low energy components, the dosimeters would not perform good, but would have overestimations of the true value of the quantity HP. Here we see work from a large dosimetry service in Europe, which is published in Radiation Measurements, where the authors have shown the response of the dosimeter in blue to the HP10 quality, as we have it nowadays, and to HP. And obviously you see this high overestimation, and they have been generous. They cut off the plot, so you don't have to go up to 5, but I know it goes up to 5, these values here. And then the lighter curves in this plot are the use of different filter materials on the dosimeter than the standard Teflon filter. And on the right side, there are modified evaluation algorithms because the dosimeter has 2 detectors and one can change the ratio of evaluation between these 2 detectors. And you see that they improve the situation somewhat until a certain energy where then it cuts off still. But this is, I would say, this is first work which has been done recently. And before these new quantities become legally binding quantities, there will be enough time to do more work of development and research to adapt dosimeter types to them. Here's the response of survey instruments. There the picture is much better. Survey instrument based on a Geiger-Müller counter. This is a handheld device which has quite a rugged casing and which simply cuts off gamma rays below 50 keV. And you see the response curve under H star and under H star 10. And you can imagine that you can simply at the reference point recalibrate and the 2 curves will cover each other. The same is true for an instrument based on ionization chambers where the response is cutting off even earlier. These are ionization chambers which are filled with high pressure gases and therefore have 1 centimeter or even more wall thickness of stainless steel. So they really cut off low energy gamma rays and they can be simply recalibrated without loss of usefulness in their approved measurement range. Neutron monitors is another chapter. I have here a plot from a publication from John Eakins and co-authors from the Physical Health England, although I heard that they just changed name again, published in 2018 already. And they show here the response functions of Rem-counters for the quantity H*10. And I would like to highlight that already with the present quantity H*10, the response of Rem-counters is everything but smooth or ideal. It moves between 0.2 and a factor 10. And the IEC, which gives acceptance levels for good instruments, has defined these black levels here, which are the acceptance regions, acceptance levels depending on energy for suitable Rem-counters. You see that they are very wide until 100 kV, then they become a bit narrower, and then they have to be widened again at 10 MeV. When you now convert these response functions into the one for the new quantity, you see that the whole family of curves seems to move upward. It's a bit more stretched in the fast neutron energy range. And of course, it doesn't fit anymore to these acceptance levels. I suppose that what will happen for Rem-counters is that one calibrates them as usual with radioisotope sources, introduces a coefficient to lower the response, and then the IEC will have to discuss in how to adapt the acceptance regions to the new quantity. I don't think that we really face a much worse measurement in the future than nowadays of neutron dosimetry. I come to the summary for dosimeter response. So area dosimeters with a cutoff energy of more than 50 kV are nearly unaffected, and one can recalibrate their sensitivity. I should have said photons. Extremity dosimeters, no changes are needed. Lens dosimeters are nearly unaffected. Maybe a slight recalibration is necessary. Our real problem case are the whole body dosimeters, which show an over-response at low photon energies. And here it is necessary to invest some research into a redesign of the filter package or the algorithms for multi-detector types. And finally, neutron monitors continue to give good estimates of the neutron dose or neutron dose equivalent, and they will have to be recalibrated, and the IEC will probably readapt the acceptance limits that it has defined previously. And I'm already at my last slide. I hope that I was able to show you that the new operational quantities are defined in a consistent manner to the protection quantities by using the same phantoms and the same weighting factors. This makes the system of quantities in radiation protection easier to understand. The numerical values and their trends with energy are also coherent with the protection quantities. The changed dose values in real radiation fields do not warrant change of radiation protection practice. This should have been a P. You have seen that in accelerator fields, the new quantities will probably give dose readings of 20% higher than present ones. In radionuclide fields, 15% lower. This is not something where we need to change a lot our practice. The study is required and is done actually for fields in interventional radiology. The calibration procedures remain unchanged. One simply has to use the new conversion coefficients and, as usual, realize the secondary electron equilibrium for gamma radiation, and then use the conversion coefficients from the annex of the ICRU report. And yes, the difficult chapter is that whole body personal dosimeters for gamma and beta radiation at low energy will need some clever ideas to adapt their response to the new quantity. Thank you very much for your attention, and I'm available for questions.
Okay, many thanks, Thomas. Many thanks for your very clear, interesting talk. So.